Word ladder. This is the graph problem interviewers love. Word ladder. It looks like a toy puzzle, change one letter at a time, but secretly tests BFS instincts, hashing, and pre-processing. This Pattern Mastery 100 favorite appears at Meta/Amazon screens because many candidates brute force neighbors and time out. We'll blitz it with basic and finish in clean on middle.l squared, or better with bidirectional BFS. We're given begin word, end word, and a word list. Each step you can change exactly one letter, and the new word must exist in the list. Return the length of the shortest transformation sequence from begin word to end word, counting both ends. If impossible, return 0. Shortest number of steps in an unweighted graph? That's BFS. But we can't build edges naively, too slow. Instead, pre-process using generic patterns. For each word, replace each position with two form keys like HT or IT. Words sharing a key are one edit apart, then BFS from begin word using this pattern map. Complexity. Build map in on middle.l keys and traverse neighbors in on middle.l squared worst case. For extra speed, we can run bidirectional BFS from both ends. If end word not in the list, return 0. Put all words into a set. Ensure begin word is included for pattern generation. Build patterns. Dict str, list str, by replacing each position with standard BFS, Q holds, word, distance. For each popped word, iterate its patterns and neighbors, in queue unvisited neighbors at dist +1. Mark visited as soon as in queued. Let's wrap up the word ladder problem. Now let's solve solution 1. We're walking through the word ladder problem using a single direction BFS approach. I'll break everything down line by line, explain it in simple language, and guide you through how the algorithm works step by step. Time complexity is ONM26, where n is the number of words in the word list, m is the length of each word, and 26 is the number of possible letter substitutions we try at each position. The idea of BFS for word ladder: treat each word as a node in a graph. Two words are connected if they differ by exactly one letter. Use BFS to explore level by level. As soon as we reach the target word, that level count is the shortest transformation length. The goal is to change one letter at a time until you reach the end word. Line by line explanation of the code. First, we import deck. This gives us a fast queue structure that lets us pop from the front quickly, perfect for BFS. We create a class called solution. This is the standard format when submitting problems to LeetCode. This defines our function. It will compute the shortest transformation steps from the starting word to the target word. We convert the list of words into a set. This makes checking if a word exists super fast. Instead of searching through a list, we just ask the set. We check if the end word is even reachable. If the end word isn't inside the list, then there's no way to transform into it. We return 0 immediately, meaning no possible transformation. We create our BFS queue and start with the beginning word. This is the first word in our search path. We track words we've already visited so we don't repeat and cause loops. We set the starting level to 1. The begin word already counts as the first step. As long as there are words in the queue to explore, we keep going. That's the core of BFS. We process all words in the current level before moving deeper. This is how we count transformation steps correctly. We take the next word from the queue. This is the word we'll try transforming. If this word is already the target, we're done. We return the number of steps taken to get here. BFS ensures this is the shortest path. We look at each position of the word, preparing to replace one letter at a time. We test all 26 possible letters for that position. This simulates every allowed single step change. We build the new word by swapping the character at position I with the letter C. We check if this new word is part of the allowed dictionary and if we have visited it already. If it's valid and new, we can explore it. We mark this new word as visited so we don't process it again. We add it to the BFS queue for the next level of exploration. When we finish exploring all words in the current level, we increment the step count before moving to the next. If we finish the entire BFS without finding the target, we return 0, meaning no valid transformation path exists. And that's how this algorithm works. It first builds the BFS setup, then explores all possible one-letter transformations level by level until it reaches the target. It's clean, predictable, and efficiently finds the shortest path. BFS guarantees the shortest transformation sequence. Each word can branch into up to 26 times word_length possible neighbors. Using a set ensures fast lookups. Worst case time complexity is ONM26. Now that we've implemented our BFS solution for the word ladder problem, it's time to test it with an actual input. This step shows how the algorithm behaves in practice and ensures that our logic produces the correct result. We will walk through the input, observe how the solution processes it, and confirm that the output matches what we expect. Let's test our function using this input. We have a starting word hit, a target word cog, and a dictionary of words that we can use to transform hit step by step into cog. Here's why the solution works. The algorithm uses a breadth-first search to explore all possible single-letter transformations from hit. It keeps track of visited words to avoid repetition. Step by step, it finds the shortest sequence of transformations leading to cog. For example, the chain hit hot.dog gives a total of 5 steps, which is the shortest path. And that is exactly what the program outputs. 5. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully finds the shortest transformation sequence between the start and end words. It handles the given input correctly and produces the expected output. BFS ensures efficiency, avoids unnecessary repetitions, and guarantees the minimal path. This is solution 2. Finding the shortest transformation sequence between two words using bidirectional BFS. We expand from both the start and end words simultaneously, checking for overlaps. Time complexity is O(n)m, faster in practice, where n is the number of words in the list and m is the length of each word. Bidirectional BFS reduces the number of levels explored compared to standard BFS. We import deck to efficiently perform queue operations for BFS. We define a class solution to hold our method. The function ladder length computes the length of the shortest transformation sequence from begin word to end word. Convert the list of words into a set for O1 lookups. If the target word isn't in the list, return 0. Initialize sets for BFS from both ends. Begin underscore set containing begin word, end underscore set containing end word. Initialize a visited set with begin word and set length equals 2 to start counting the sequence. While both frontiers are non-empty, always expand the smaller frontier to reduce the number of iterations. Swap begin underscore set and end underscore set if necessary. Initialize an empty set next underscore set for the next level. For each word in the current frontier, for each character position, try replacing it with letters A to Z to form new potential words. If the new word exists in the opposite frontier, the searches have met. Return the current length. If the new word is in word set and not visited, mark it visited and add it to next underscore set. Replace begin underscore set with next underscore set and increment length by 1. If BFS completes without meeting the two ends, return 0. No valid transformation exists. Bidirectional BFS reduces levels explored compared to standard BFS. Each word generates 26 length transformations at each step. Worst case complexity is O(n)m, but it is practically faster due to reduced search space. Before checking the output, let's understand the problem. We are given begin word equals hit end word equals cog word list equals hot.dog log. The goal is to find the shortest transformation sequence from begin word to end word, changing one letter at a time, using only words in the list. If no path exists, the function should return 0. Let's test our function with this input. Here, cog is not reachable from hit using the given words. Here's why the solution works. Bidirectional BFS. Start from both begin word and end word to expand towards each other. Always expand the smaller frontier to optimize search. Generate neighbors. For each word in the current frontier, try changing each letter from A to Z. Only add new words if they are in the word list and not visited. Check for meeting point. If a new word appears in the other frontier, a path is found, return the current length. If no path is found after exploring all possibilities, return 0. Step by step with this input. Hit hot, possible, hot dot or lot.dog log, but cog is missing in word list, so the frontiers never meet. The function correctly returns 0. And that is exactly what the program outputs, 0. This confirms that the code handles cases where no transformation path exists. So, our implementation is correct. It successfully identifies when a word ladder is impossible, efficient, accurate, and reliable. Our implementation is correct. It correctly identifies when no path exists. It efficiently searches using bidirectional BFS. It returns the correct shortest length when a path is possible, or 0 if impossible. Let's wrap up the word ladder problem. At first glance, it seems like a simple word game. changing one letter at a time. But underneath, it's a classic graph challenge that really tests your BFS intuition. Breakdown recap. We started with the idea of transforming a begin word into an end word, step by step, where every new word must exist in the list. Our goal was to find the shortest path from start to finish, and if it wasn't possible, we'd return 0. Assess recap. To solve it efficiently, we recognized that this was a shortest path problem in an unweighted graph, perfect for BFS. Instead of brute forcing every word connection, we optimized using pattern pre-processing, where we replaced each letter with a wildcard, creating keys LeetCode or it to group words that differ by just one letter. Structure recap. From there, we structured our approach. First, check if the end word exists in the list. Then, build all pattern mappings and perform BFS to explore word connections layer by layer, counting each transformation step until we reach the target. Implement recap. After implementing it, we ran the code on LeetCode, no errors, smooth execution. Check recap. When we tested it with multiple cases, the outputs matched perfectly, confirming our logic worked as expected. The big takeaway? Word ladder isn't just about words, it's about recognizing graph patterns and using BFS smartly. Once you see that connection, the path to the solution becomes crystal clear.